Welcome to the deep dive. Today we're going to peek under the hood of a pretty sophisticated energy system model. We want to see how it crunches the numbers to optimize, well, everything from maybe your heating at home to entire power grids, all aiming for a more sustainable future. We're diving into this fascinating, intricate world of energy system modeling specifically, how this model makes these crucial calculations, fuel use, CO₂ emissions, managing electricity flow.
Exactly. Yeah. If you've ever wondered how decision makers actually assess these really complex energy scenarios, whether it's, say, managing power plants or your local district heating system, this deep dive should hopefully illuminate the logic underneath it all. We're getting into the core calculations, the ones that ensure energy stability, manage any surpluses, and track the environmental impact, and of course the costs.
Right. And we've got sources here detailing the specific calculations of one such model. It's designed to optimize energy production units, looking at both technical strategies and market economics. It really feels like a proper deep dive into how these integrated energy systems actually work behind the scenes. So what's our mission today then?
I'd say our mission is to really pull back the curtain, see how a model like this performs the heavy lifting. Things like managing excess electricity, ensuring the grid stays stable, balancing these complex gas flows, and precisely calculating fuel use, emissions, costs. We'll try and show you how the system accounts for basically everything from, say, a boiler breaking down unexpectedly to the future potential of hydrogen export.
Okay, great. With that mission, let's dive straight into the nuts and bolts. You mentioned the model optimizes operations first, but what calculations does it actually perform after it figures out that optimal plan?
Okay, so once it has that optimal operating plan, the model immediately gets into calculating the final fuel consumptions, the resulting CO₂ emissions, and the overall costs. And critically, it also tackles something called critical excess electricity production, CEP for short. But actually, before we unpack C, there's a practical detail worth mentioning. It's about reliability. The model accounts for what's called fixed boiler production. This basically covers times when maybe a combined heat and power unit, a CHP, is down for maintenance or breaks down, and make sure the system can still meet heat demand reliably, even if a key part is offline.
Okay, that makes sense. Reliability is key. But this critical excess electricity production, CEOME, that sounds like a pretty big challenge for grids today, especially with more renewables. You've got all this valuable electricity, but maybe nowhere for it to go right at that moment. How does a model like this actually strategize to reduce that surplus?
Yeah, CEP is essentially electricity produced beyond the immediate demand. And managing it is, well, it's absolutely key for efficiency and for grid stability. The model has quite an impressive arsenal, actually. 9 distinct measures it can use to cut down CEP. And what's really interesting here is they're not just like random options. They can be activated in any specific prioritized order.
Prioritize. How does that work?
Think of it like a pre-programmed playbook for dealing with excess energy. So if the input is, say, 315, it means the model first tries option 3 to reduce CEP, then it tries option 1, and then option 5 in exactly that sequence.
Ah, I see. So it's strategic.
Exactly. It's a powerful way to prioritize certain solutions, maybe based on cost or environmental impact or what the grid needs right then.
9 options.
Mm-hmm.
That's quite a toolkit. What are some of the most common ways, or maybe the most innovative ways, it tackles this CE?
They cover a really wide spectrum, actually. One common approach is reducing specific renewable energy sources, RES, so, dialing back large wind farms or solar PV when there's a surplus.
Right, curtailment.
Exactly. Then another is reducing combined heat and power, CHP, production in certain groups. Often that involves replacing the heat generation with maybe less efficient but more flexible dedicated boilers.
Okay.
Conversely, it can do the opposite. It can replace boiler production with electric heating, basically using that excess electricity as heat, which is, a pretty clever way to absorb surplus power.
Yeah, demand-side response almost.
Sort of, yeah. And then perhaps one of the most forward-looking options, and this is where it gets really interesting, is increasing hydrogen production for export during those CEP hours.
Hydrogen. Wow.
Yeah, it effectively converts surplus electricity into a fuel you can store and export. The model prioritizes using available electrolyzer capacity for this. So it's not just cutting waste, it's actually turning what used to be waste into potential value.
That's fascinating. What else?
Well, there's also a very nuanced strategy. It involves reducing power plant production in combination with renewables.
In combination. Why is that needed?
Because sometimes, especially with very high renewable shares, you might actually need to increase power plant output just for grid stability, for inertia or frequency control. But doing that might then create CE from the power plant itself.
Ah, okay. A tricky balancing act.
It is. So this option lets the model decrease both the power plant and the RES production simultaneously, maintaining stability while still trying to use as much renewable energy as possible.
Makes sense.
Then there's another innovative one, increasing CO2 hydrogenation during SEEP hours.
CO₂ hydrogenation.
Yeah, where captured CO2 is combined with hydrogen, maybe hydrogen produced from that excess electricity, to make additional synthetic gas for the grid. It leverages available plant capacity, so you're turning two potential waste streams, CO2 and excess power, into a valuable fuel.
Incredible. Any others in the list of 9?
And finally, the model even includes the capability for part-loading nuclear plants. So it allows them to reduce their output during SEEP hours if there's technical potential for them to ramp down based on a user-defined share of their maximum capacity. That adds another layer of flexibility.
Okay, so these really aren't just abstract ideas. They represent real-world dynamic strategies for balancing a grid that's constantly changing.
Yeah.
But managing excess power, CEP,
Yeah.
that's just one piece of the puzzle, right? The real test of any energy system is stability. How does the model ensure the lights, stay on?
Absolutely. Beyond CP, the model performs several other essential system-wide calculations that directly impact stability. Grid stabilization is paramount, obviously. The model calculates the total grid stabilization demand based on the total electricity production. Then it calculates the actual supply of stabilization services from various sources, power plants, CHPs, even some renewables can contribute now. And the fulfillment is then presented as a percentage. So it indicates precisely how well the system is meeting its stability requirements. If that percentage dips too low, it flags a potential problem.
Okay, a direct measure of stability.
Exactly. It also meticulously determines the heat balances in district heating systems, making sure the demand for heat from, homes and businesses is met by this diverse mix of sources: solar thermal, CHPs, heat pumps, traditional boilers.
Got it.
Then we get into fuel consumptions. The model specifies how different units, power plants, CHPs, boilers, use various fuel types: coal, oil, natural gas, biomass. And what's interesting here is you can specify certain fuel types as fixed in their consumption.
Fixed, like a policy requirement.
Exactly. So for instance, if policy dictates you must use a certain amount of biomass, the model then intelligently shuffles the shares of the other fuels like natural gas or coal to meet the total energy demand. It really reveals the subtle ripple effects of those policy choices.
That's useful.
And it also includes renewable energy wind, PV, solar thermal as a kind of new fuel type in its overall fuel accounting, corrected for imports and exports, which is, I think, a progressive way to view energy input.
Yeah, treating renewables as an input resource.
Precisely. And then CO2 emissions are calculated pretty directly, just multiplying the fuel consumption by the specific emission factor for each fuel type, again, adjusted for imports and exports.
Okay, so it covers electricity, heat, fuels, emissions.
Yeah.
But this raises an important point. What about the gas grid itself? Good question. Natural gas is still a huge part of many energy systems, gives a lot of flexibility. How does this kind of system model manage the complexities of the gas grid, especially with different types of gas emerging?
Yes, the gas grid. The model really does drill down into balancing it. It tracks both traditional natural gas consumption and the production of renewable gases like biogas and syngas. So first, it identifies all the natural gas consumption from a huge array of sources. You've got boilers and district heating, CHP units, big power plants, even compressed air energy storage CES facilities that might use gas for reheating.
Right.
Plus, individual gas boilers, micro CHPs, natural gas vehicles, various industrial uses. It sums all that up to get the total natural gas demand.
Okay, comprehensive list.
Then, on the supply side, it tracks biogas and syngas production. Biogas from anaerobic digestion plants is calculated, and its supply to the grid is determined after it's upgraded, cleaned up to pipeline quality.
Okay, biomethane, basically.
Exactly, biomethane. And after subtracting any amount that might be used locally, maybe for making electrofuels, syngas production from gasification plants is also calculated, and the model might use maximum capacity flexibility there to try and minimize external gas imports on an hour-by-hour basis.
Trying to be self-sufficient where possible.
Right. And crucially, the model can use gas storage capacity to dynamically balance the whole system. If storage is specified as available, it actively manages the flow into and out of storage every single hour.
Every hour. Wow.
Yeah. It'll fill storage when there's an excess supply, maybe from that biogas or syngas production, and then draw from it when demand spikes higher than the immediate supply. This helps smooth out the import-export profile over the whole year. It even repeats this calculation iteratively until the storage level at the end of the year matches the start.
So it ensures the storage isn't artificially depleted or overfilled in the simulation.
Precisely. It finds a sustainable cycle. And finally, based on all these flows, demand, renewable gas production, storage movements, it determines the overall balance and therefore the necessary import or potential export of gas for the entire system.
That level of hourly detail for gas balancing, it sounds incredibly complex. Does that kind of granularity reveal surprising things, efficiencies or bottlenecks you wouldn't see otherwise? And of course, the bottom line for any real-world system, cost. How does the model assess the financial side, the true socioeconomic costs of running such a complex system?
That detailed balancing is absolutely key to revealing those subtle interactions and potential efficiencies. Yeah, the computation can handle it. And you're right, cost is a critical output. The annual socioeconomic costs are broken down into several main categories. First, fuel costs. Pretty straightforward. The input unit prices, including any handling costs, multiplied by the total annual consumption of each fuel. And importantly, the model focuses specifically on socioeconomic costs here. So taxes aren't included. It gives a clearer picture of the underlying resource costs.
Right, the cost to society, not just the market price with taxes.
Exactly. And you can see detailed calculations for each fuel type, like how the total annual coal cost is built up from consumption in power plants, CHPs, etc.
Okay, what else?
Then you have electricity exchange costs. These are based on external market prices. The cost of importing electricity is simply the hourly import amount multiplied by the market price at that hour. Income from exporting is calculated the same way. It also accounts for something called bottleneck income.
Bottleneck income.
Yeah, this happens when the transmission lines connecting regions are maxed out, fully exploited. If there's a price difference between the external market and the internal simulated price, that constraint creates a kind of congestion rent or income.
Ah, interesting. A market signal from the grid constraint itself.
Precisely. Then there are variable operational costs. These are calculated per unit of production for relevant units. So, for example, the operational costs for boilers would be their total heat production multiplied by their specific variable O&M cost per unit of heat.
Okay, costs that vary with output.
Right. And finally, you have the fixed operation and maintenance, O&M, and investment costs. These are usually predefined inputs, maybe from a separate data sheet. They represent the fixed annual costs you have, regardless of how much the plant actually runs things like staffing, insurance, and annualized investment costs.
It really is impressive how all these calculations interconnect. It definitely seems to paint a complete picture of the system's performance. You've got operational efficiency, environmental impact, financial viability. It really ties it all together. So after unpacking all this detail, what does this all really mean for how we understand our energy future?
Well, what becomes really clear, I think, is that future energy stability isn't just going to be about building more power plants or more wind turbines. It's about this incredibly complex, almost invisible dance that these models help us choreograph. Their ability to simulate all these different strategies for managing CE, for integrating diverse fuels, balancing gas grids, tracking costs meticulously. It means they are just powerful, really indispensable tools for analyzing the energy transition. It shows that optimizing an energy system isn't just about producing enough power. It's about doing it efficiently, cleanly, cost-effectively, really leveraging every last watt and molecule to balance everything, even, as we saw, potentially turning waste CO₂ into fuel.
Yeah, that's our deep dive into energy system modeling.
Okay.
It really gives you an appreciation for the sheer complexity behind just keeping the lights on and our homes warm, and how crucial all this detailed data and these sophisticated calculations are for actually building more sustainable energy futures.
And maybe, if we connect this to the bigger picture, it raises a question, doesn't it? As our energy systems become even more interconnected, more reliant on variable renewables, maybe more distributed, how might the next generation of these models need to adapt? How will they incorporate even more dynamic resources, maybe right down to the neighborhood level, or even individual smart homes interacting with the grid?
That's definitely something to think about as you contemplate your own energy use.
Yeah.
We hope this deep dive has given you a useful shortcut to being well informed about this really fascinating world of energy system optimization.